Hi, welcome to our virtual glaucoma conference. My name is Mary Durbin, and I am the Director of Clinical Research and Analytics Development at Carl Zeiss Meditech. The next hour will include presentations from 7 ZEISS scientists who are working as part of our R&D team to develop new capabilities for our ophthalmic imaging devices. This work is based on presentations we created for ARVO this year and in previous years. The scientists and engineers at ZEISS had more than 50 abstracts accepted for ARVO and ARVO imaging in the eye, and we selected a few that we thought you would be interested in. Our first 2 presentations are not directly related to glaucoma, but address measurements on the eye that are related to how we measure and manage glaucoma. In the first presentation, Niranjana Manivanan, a senior staff scientist, demonstrates that machine learning can be used to estimate values such as axial length from fundus images. These biometric values are known to impact measurements used in glaucoma. For instance, we know that RNFL thickness is thin in long eyes, and therefore normative data is not applicable, which can sometimes make managing myopes a little bit difficult. Estimating the axial length directly from a fundus image could mean that you don't need an IOL master data set and may allow you to correct this issue in a clinically practical way. In the next presentation, Kat Foote, a senior clinical scientist, will show that our CLARUS fundus imager could potentially be used to measure peripheral refraction across the 90-degree field of view of the image, which might be used in studying the development of myopia. And then, once you study the development, maybe developing treatments for it. We felt this might be of interest to a glaucoma audience since myopia is both a risk factor for glaucoma and something that complicates the measurement and management of glaucoma. So then we will move to presentations that are directly related to glaucoma. Another senior staff scientist, Gary Lee, will present on a really interesting potential use for deep learning, which builds on the idea of using a prior glaucoma visual field to seed the test thresholds in today's visual field to allow us to finish the test faster by starting at the best values for that patient. But what Gary did was to try using an OCT scan, which could be a prior scan or it could be today's scan, as an input to the test starting thresholds in order to shorten the overall time. So we think this could be a very exciting application of deep learning in an innovative way. The next presentation will move to the other side of the structure function capabilities, that is, analyzing the results. Sophia Yu, another member of our clinical research and analytics team, will evaluate the repeatability of a metric that was designed by Professor Felipe Medeiros, and it's called the Retinal Ganglion Cell Index, or Rgci. Visual fields and optical coherence tomography are both important diagnostics when evaluating glaucoma, but they have different strengths and weaknesses that change with the stage of the disease. The Retinal Ganglion Cell Index takes advantage of the strengths and minimizes the weaknesses, creating a combined index that gives the doctor a single number to follow over time. It is critical that a metric like this be repeatable on repeated tests, and Sophia will use clinical data that we collected to demonstrate that in fact it is repeatable and could potentially be a good way to monitor glaucoma across time using both structure and function. You may have heard that ZEISS recently introduced the new CIRRUS 6000, which scans at 100 kilohertz instead of 27 kilohertz. Traditionally, such an increase in speed would be accompanied by a reduction in signal, but we also took advantage of several hardware improvements to keep the signal the same. The end result is that structural measurements remain the same between the 2 models of CIRRUS, even though the scan is done more than 3 times as fast. Catherine Makadonsky, an optometrist and member of our clinical research team, presents clinical evidence for this comparability in retinal nerve fiber layer measurements. This shows that ZEISS is committed to helping you manage your patients over the long term, even while improving technology. Moving back to the functional measurements, Dr. Tom Callan, one of our most senior clinical scientists who also teaches at the Berkeley School of Optometry, describes the development of a new test pattern, the 24-2C, which adds 10 central test points to the traditional 24-2 pattern. This allows improved sensitivity to loss in the central part of a patient's vision, a topic of increasing interest in the field. Of course, the central part of the field has always been important for the patient's quality of life. We implemented these new test points with our SITA Faster test strategy in order to get this important new information while keeping test times as short as possible, because we know visual fields take a long time. The final presentation is from Gregory Anderson, a senior staff human factors engineer and user experience lead. This presentation looks at the effects of response style on SITA standard 24-2C and SITA Faster 24-2C visual field tests. We all know that some patients are trigger happy and some are good test takers. Learning about how our individual response styles affect these important tests may help us design tests that are well suited to each individual rather than one size fits all. We hope you enjoy these presentations and find them an interesting view on the innovative work being done by ZEISS scientists. Thank you for watching and attending this virtual session.
Thanks everyone for coming to my talk. I'm Niranjana Manivanan, and I'm a research scientist in advanced technology and concepts in ZEISS Meditech. Here are the disclosures for everyone involved in the study. The main aim of the study is we are trying to predict axial length and refractive error by leveraging focus settings from wide field fundus images. Recently, deep learning has been used for predicting more than retinal information from fundus images. For example, like age, blood pressure, gender, etc. In this pilot study, we wanted to see whether we can predict axial length and then the refractive error from the fundus images. So why are we using focus setting? The main bottleneck for training these kind of deep learning algorithm is availability of the data. Getting a large data set with fundus image and then associated axial length and then the spherical equivalent can sometimes be difficult. So we are using an intermediate parameter called focus setting of the camera. Why we decided to use the focus setting of the camera is usually focus setting is related to refractive error, and axial length is regarded as one of the determinants of the refractive error. Hence, because all three of them are correlated, we decided we would use focus setting as an intermediate step for training the algorithm. For this, we took a retrospective data of 5,291 wide field true color images from CLARUS, along with the focus setting in diopter, which is recorded during the acquisition. Then the model was trained to predict the focus setting. For the second part of the algorithm, we collected axial length from 162 CLARUS images by using IOL master. And for predicting spherical equivalent, we used 367 images along with spherical equivalent of refractive error by using VisuRef. For testing both of these parts of the algorithm, we used 41 images with corresponding axial length and 94 fundus images with corresponding spherical equivalent. The algorithm is trained in two steps. The first step is finding the focus setting. The second step is the transfer learning to predict axial length, and one more transfer learning to predict the spherical equivalent. We used a modified 3-channel ResNet 50 with softmax activation for the algorithm framework. For measuring the performance, we used mean absolute error. The final results of the model show the model trained to predict the axial length has a mean absolute error of 0.61 plus or minus 0.41 millimeter. The results are shown in the table 1. The transfer-trained algorithm for predicting the spherical equivalent had a mean absolute error of about 0.73 plus or minus 0.56 diopter. Figure 1 shows some of the results of the proposed algorithm. So in this pilot study, we used a focus setting to do transfer learning to find axial length and refractive error from the fundus images. In the future, these deep learning methods may provide solutions to customize the measurements in the fundus camera, because currently most of the measurements in the fundus camera follow an average eye optical model. If we have the correct axial length, then in the future, we might be able to enable customized measurements using this axial length. Thanks everyone for listening to the talk.
My name is Katarina Foote, and I'm a senior scientist in the Advanced Technology and Concept Group at ZEISS. Today, I'm going to present a poster on ultra-widefield peripheral refraction using a slit scanning ophthalmoscope and image montaging. High myopia is considered to be a risk factor for, as well as a comorbidity in the diagnosis of glaucoma. Ultra-widefield retinal imaging has proved useful in the diagnosis of disease where visualization of the periphery is vital, including high myopia. Peripheral refraction, or the measurement of refractive error at areas in the peripheral retina, can be of interest to researchers studying myopia. Although commercially available, open field autorefractors can be used to measure peripheral refraction, a wide field slit scanning ophthalmoscope can potentially perform such measurements faster and with more ease of use. Peripheral refraction is of interest in the pathogenesis of myopia, and ultra-widefield imaging can provide a suitable way to increase measurement areas. We performed a prospective study in order to investigate the feasibility of the use of ultra-widefield imaging to extend the angular range of measurement for peripheral refraction. 4 subjects ranging from -12 to -0.5 diopter spherical equivalent refractive error were scanned on a wide-field slit scanning ophthalmoscope. The internal fixation target was moved to enable data capture over multiple overlapping 90-degree fields. Prototype software was used to calculate the vertical component of peripheral refraction over each field, co-register the fields based on matching fundus features, and then merge them together in order to derive peripheral refraction over 130 degrees along the horizontal meridian. Ultra-wide field peripheral refraction measurements provided an extended view of peripheral refraction for emmetropic and myopic subjects. Figure 1 displays examples of ultra-wide field absolute peripheral refraction in 2 highly myopic eyes. Here, cooler colors indicate refraction trending towards hyperopia, whereas warmer colors represent refractions in the direction of myopia. Figure 2 shows the relative peripheral refraction along the full horizontal meridian, which was averaged over a vertical extent of 1 degree for each of 4 subjects. All curves show the characteristic of relative hyperopia peripherally. The effect is more pronounced for subjects with higher myopia than for more mildly myopic subjects. In conclusion, a slit scanning ophthalmoscope is capable of providing ultra-wide field measurements of peripheral refraction. This method could further the study of myopia development and progression through analyzing effects of refraction in the far periphery. Thank you.
I'm Gary Lee from ZEISS, and I'm a scientist in ZEISS's Research and Development Group. I'm a team leader in the area of concept development for glaucoma and visual field algorithms and applications development. So on behalf of myself and my co-authors today, I'd like to share some of our research with you regarding the performance of simulated visual fields using structure-derived prior information. Here are our affiliations and financial disclosures. So the last few decades have seen dramatic improvements in visual field test times and accuracy. And one way that modern thresholding strategies have achieved this is by using prior information based on population or reference database results. Separately, it is also well known, especially in glaucoma, that structure and function are typically highly correlated. Therefore, we wanted to explore the possibility of leveraging the structure-function relationship plus AI techniques to accelerate visual field exams. In this proof of concept study, we evaluated the performance of using visual field priors derived from structural information, i.e. what we call S priors in simulated visual fields. So the data we used in this study was retrospectively taken from a Singapore population study containing about 1,400 eyes of 1,400 subjects. 24-2 visual fields and 200 by 200 optic cube scans were acquired at the same visit from HFA and CIRRUS respectively. We split the data 70 to 30% for training and testing purposes. And the training data was used to train 2 types of AI models to predict the visual field S priors from the OCT data. First, a classic random forest regressor was trained using RNFL thickness T-SNP profiles and subject ages as inputs. That is, we took the T-SNP profiles and created the visual field S priors, as you see blinking on the screen. Second, a simplified mixed scale dense convolutional neural network, or CNN, was trained using the 2D RNFL thickness maps as inputs. And that is, we used the 2D RNFL thickness maps to create those visual field priors. And then in the next step, the reserved 30% test data was used to either A, generate AI predicted S priors for use as individualized priors, and B, to provide true visual fields to a visual field simulator. So what does that mean? Typically, if I sat down in front of a perimeter and took a test comparable to SITA, which uses, again, pre-existing population reference data to speed up the test, in this simulation, we actually use the 24-2 visual field, or the true visual field from the study, to serve as the patient, or to represent the patient. Then the probability of response at each test location was modeled using frequency of seeing curves, which we did in this study as previously described by Henson et al. We also set false answer rates to 0%, 5%, and 20% to represent 3 different styles of responders. So kind of reliable responders to unreliable responders. For the simulations, we also implemented a Bayesian ZEISS strategy, which is a simple surrogate for modern strategies such as SITA, and that also used reference population data. Finally, then we implemented modified ZEISS to use S priors instead of population reference data, which for the rest of the slides we'll call ZEISS RF and ZEISS CNN. So the performance between the final simulated and input true visual fields were evaluated by looking at the mean absolute error, or MAE, for accuracy, and the total number of stimulus questions for test duration. Then we did equivalence tests at a confidence level of 95% to evaluate inter-strategy equivalence for both ZEISS RF and ZEISS CNN versus ZEISS. The limits of equivalence here were 0.5 dB for MAE and 5% for total number of questions. Then the mean ages in the population for the training and test distributions were 53.6 and 56.4 years for the training and test sets. And the mean visual field mean deviations were minus 1.8 and minus 2.7 dB for the training and test sets. We observed that the AI models performed better in the higher thresholds versus the lower threshold sensitivities. And this is very likely due to the fact that less than 4% of the population study data had values less than 20 dB for thresholds. So kind of a large training data imbalance. Nonetheless, for the majority of the fields in the study data in which thresholds were greater than 20 dB, the predicted S prior visual fields achieved lower MAE values. However, as you might expect, fields with deeper scotomas, such as arcuate defects, resulted in larger MAE values and S priors that were not as accurately as they possibly could have been. Nonetheless, we saw that the number of total questions was reduced 16 to 19% with the S priors, and that the accuracies for ZEISS RF and ZEISS CNN were equivalent to ZEISS within 0.5 dB. And as expected, the accuracy decreased and the number of total questions increased with increasing responder false answer rate, or as they got more and more unreliable. So overall, the preliminary findings suggest that in this particular population, even AI models with limited data used to predict the structure-derived visual field priors from OCT data can reduce the duration of a visual field exam with comparable accuracy. And we believe that with more data better representing the clinical population and with more refined AI models, performance may be further improved. And with that, I'd like to thank my co-authors, and I'm happy to take any questions. Thank you so much for listening.
Hi, my name is Sophia Yu, and I will be presenting on the repeatability of a combined retinal ganglion cell index in glaucoma. And these are my affiliations and disclosures. So why are we doing this study? We know that glaucoma is related to the loss of retinal ganglion cells. We use functional and structural testing to estimate the extent of this loss. We detect structural changes with an OCT and functional changes with visual fields. But both of these techniques have sources of error, and they work better and worse compared to each other in different stages of disease. OCT is more applicable in early disease, and visual fields are better for later stages. The Retinal Ganglion Cell Index, or Rgci, is a combined metric created by Philippe Medeiros to allow monitoring of glaucoma across the different stages. Any metric that we want to use for follow-up should have good repeatability and reproducibility. So we set out to study the test-retest repeatability for this new metric using retrospective data. The methods to estimate ganglion cell counts from functional and structural tests have already been published in the literature. Basically, the insight of Rgci is to combine these in a way that accounts for the stage of disease and then to normalize it. This provides a combined metric that can be used across all stages of disease. To study the repeatability of the Rgci, we used data collected from 74 subjects with glaucoma on repeated visits. There were 3 sites who collected data. The subjects had to return for 5 visits. At each visit, the site obtained a 24-2 SITA standard visual field on the HFA2 eye and 2 CIRRUS scans, one over the macula and one over the optic disc. The goal was to have a representative sample that included early, moderate, and severe glaucoma. The sample size of 74 was set for the study by the goal of establishing specificity in a population that was not expected to have progressed because they were seen over such a short period of time. The metrics of variability we used included test-retest standard deviation and coefficient of variation. We also looked at test-retest as a function of the stage of disease. We then compared these measures of variability between Rgci and all of the individual metrics that go into evaluating the stage of disease, such as mean deviation, BF index, and cup to disc ratio, etc. So what do we find? The table shows the descriptive statistics for the demographics and the basic summary parameters. The subjects range in age from 36 to 80, and the mean deviation ranged from negative 18.2 decibels to 1.2 decibel. The PSD and the VFI also had a reasonable range. The estimated Rgci index itself ranged from 231,000 to about 1 million. We don't expect this corresponds exactly to the number of ganglion cells in each person's eye, but it should be correlated to the extent of disease. The histogram shows the distribution of mean deviations, showing that we have a good distribution of early and moderate and a few severe diseased eyes. These tables show the test-retest in the first column for each possible parameter and the coefficient of variation in the next column. You can see that the CV of the Rgci index is 5.6% and is actually a little worse than for most of the individual parameters, but it is comparable to them. And 5.6% is still an acceptable number for monitoring the disease state over time. The last thing we looked at was whether the variability depended on the disease state, since this can limit applicability. In the end, it varies a bit, but not by very much. For very normal eyes, it can be low as 4%, but for more diseased eyes, it may be as variable as 6%. 6% is still an acceptable variability. In conclusion, we found that the Rgci had acceptable variability in a glaucomatous population. It was within the range of the individual OCT and visual field summary parameters and showed similar repeatability over the range of disease. Therefore, Rgci may be a useful parameter to stage and monitor glaucoma progression. Thank you.
Hi, my name is Dr. Catherine Makedonsky, and I'm a clinician that works for Carl Zeiss Meditech. Today I'll be talking about the retinal nerve fiber layer and the cup to disc ratio and how it compares between the CIRRUS 6000 and the CIRRUS 5000. So the reason cup to disc ratio and retinal nerve fiber layer is important is because doctors can use these metrics as a way to determine if their patients have glaucoma. Of course, a doctor can take a look at the back of the eye using a 90 diopter lens, but that only gives us part of the story. So we're able to look at the cup to disc ratio, but we're not able to see the retinal nerve fiber layer. So OCT is very important to give us that metric. With glaucoma, the nerve will change first in terms of the size of the cup compared to the disc. And then the thinning of the retinal nerve fiber layer begins. After that, the visual field loss can be seen. So it's very important to catch glaucoma early in patients because there's no symptoms. So in this presentation, we'll just be discussing how the two devices compare to each other in terms of the metrics that are given by the devices. So we'll just go over the abstract that I presented here. So one of the aspects that the devices do provide is that there's a normative database. So which means that at a certain age, it's normal to have a certain thickness of the retinal nerve fiber layer and a certain cup to disc ratio. So we specifically wanted to see how the thicknesses compared to the normative database as well as between the devices. So the important thing to note is that the devices differ in terms of speed. So the CIRRUS 6000 scans at a much faster rate compared to the 5000. So the speed is 100 kilohertz compared to 27 kilohertz. So we wanted to ensure that despite the faster speed, that the metrics still stayed the same. So we evaluated about 20 normal patients using both of the devices. The mean age was 40 years. We took a 200 by 200 optic disc cube scan on the patients. So upon reviewing the results, we compared using bland Altman plots as well as linear regression. So as you can see here, the two devices do end up correlating with each other very well. And so the dots are shown very close to this line here, as well as on the bland Altman plot here. As a result, with such close correlation, we're able to conclude that the two devices are very similar to each other in terms of the results that they give. And any differences that are seen are statistically insignificant. The average time for scanning was much faster on a 6000 compared to the 5000 by about 41%. And in terms of the reports that you could see over here, this is the same subject that we are evaluating here. And actually the numbers that we're getting for the retinal nerve fiber layer and the cup to disc ratio are virtually similar between the two devices and pretty much the same here for this patient. This, as a result, concludes that the 6000 can be used on the same patients that the 5000 had been used as well as the 4000 in the past, and using the same normative database throughout. So the reason why that's great is because now with the CIRRUS 6000, you're scanning at a much faster rate, so it's more comfortable for the patient and your scans are much better because you have less blinking and things going on, but the analysis that you're getting and the results are matching to what you had been tracking them with in the past. And glaucoma is a disease of change, so it's important to track patients for many, many years. So of course, if you tracked them before with the 4000 and you upgraded to 5000, you can upgrade to 6000 with the confidence that you'll still be able to track that patient accordingly. Thanks.
Hello, my name is Thomas Callan. I'm part of the clinical and analytics development group at Carl Zeiss Meditech. I'm going to discuss a study that was done in the past year or so pertaining to the SITA 24-2C visual field test. I'd like to thank my collaborators that helped with the study. They're listed here, and here are all of our disclosures. Over the last 10 years, we've seen a trend towards trying to get more information out of the central visual field. It's been discovered that more patients are being found with small, subtle defects. A lot of that has to do with measuring the ganglion cell layers with OCT and trying to get the functional equivalent with a 10-2 test. But the issue with doing a 10-2 test is it runs longer than the 24-2 test. It's tough to ask a patient to do both a 24 and a 10-2 test on the same visit because it's going to be twice as long. And the other thing is, of course, you can't really bill for both on the same day. So ZEISS has gone ahead and worked to create a 24-2C test, which is a hybrid of the two tests. And the idea is you take a 24-2C test and add a few extra points. My colleague Gary Lee worked with Don Hood and a number of other investigators around the world, and particularly Don Hood's group in New York, to try to choose, well, what 10 points out of a 10-2 test would you use? And you can see these on the right-hand side showing which ones were chosen. And those were added to the 24-2 pattern to create a 24-2C test. Now, ZEISS put that out running on the SITA Faster strategy. So it's a relatively quick test, even though it has 10 more points than the 24-2. And the other important thing to note is that those 10 extra points are run at the end of the test. And that's important to keep the unique 24-2 test for utilization in the GPA analysis. And we'll talk about that in a little bit. So the actual study involved having a number of normal and glaucoma subjects tested on 3 and 4 different types of strategies over 2 visits. So with that information, we were able to determine that looking at the central 10 degrees of a standard 24-2 test versus a 24-2C, with normals, we didn't find much difference. As a matter of fact, no significant difference. With patients with glaucoma, though, we found that a few extra points were flagged in both the total deviation as well as the pattern deviation plots on the 24-2C. So those extra 10 points pointed out some visual field loss that wasn't being picked up on the 24-2. The other thing that was looked at were specifically the points between the threshold 10-2 and the 24-2C. So comparing the 10 points for each of those 2 tests, you were hoping for they'd be about the same. Normals, absolutely, and glaucomas, same thing. We found very little difference between the 10 points that were flagged on the 10-2 and those that were flagged on the 24-2C. So that was encouraging. Additional information gotten out of this particular study was the global indices stayed pretty much within the same range as some of the other strategies. So we have mean deviation and the visual field index shown here. The ROC curves, you can see the green lines are the ones with the 24-2C in both VFI and MD, and you can see they're right in the middle of the pack. They're not worse, they're not dramatically better. And this also included SITA Faster, as you can see, and SITA Standard and SITA Fast. So that was encouraging for the global indices. And one of the exciting things, of course, was the test time issue. Looking to create a test that runs quick enough that you can do that in addition to all the rest of the testing you need to do on your patient without slowing down the visual field area. The gray dots on the graph to the right are the faster 24-2C ones, which are take a little bit longer than the SITA Faster 24-2s, but you can see compared to the SITA Fast, blue and yellow, or the SITA Standards 24-2s, they're pretty quick. So most of the 24-2C tests in the study lasted between 2.5 minutes to 3.5 minutes, and the difference from a SITA Faster test is about 20 seconds or so, so not very long at all. Here's some examples. Here's this threshold test. Doesn't look like there's anything being found in the central portion of that visual field. The 24-2C does pick up 2 or 3 points that might be of interest, and when we look to compare to the 10-2, those correlate pretty nicely. So there's an advantage of the 24-2C picking up some central field loss that wasn't apparent on the 24-2 test. Here's another one, a little bit different way to look at it. We're expanding the pattern deviation from both the 24-2C and then the 10-2 fit pretty nicely. And so we can see that there's a nice enhancement of that central 10 degrees. Makes it a little bit easier to recognize that there may be some issues here. Mentioned glaucoma progression analysis, GPA. The 24-2C test is available to be used on GPA, even though it's faster, and sorry, a SITA Faster strategy. It can be used as baseline or follow-up visits. The big difference is, as you can see circled, that the points that are associated with the 24-2 pattern are the ones that are counted in GPA. The central 10 extra points are noted in the total and pattern deviation plots, but they're not used to calculate global indices. All right, so in conclusion, we found that the 24-2C test pattern showed good enhanced sensitivity over just a standard or regular 24-2 pattern. The corresponding 10 points seem to flag pretty nicely compared to the 10-2 test, and the test times are quite quick due to the utilizing the SITA Faster strategy. So I think we've got a good method for earlier detection of central visual field loss. Of course, doctors, if there's a concern, one can always schedule your patient back to do a 10-2 as a separate test, but I think you'll find that this will give you some extra information that you didn't have running just a regular 24-2 test. Some doctors have mentioned with the SITA Faster strategy that they're uncomfortable in the fact that it doesn't show the false negatives or the number of fixation losses in the reliability indices, as that was one of the methods that sped up the SITA Faster strategy. Here are a couple of methods of turning those back on if you're wanting to be using the SITA Faster strategy, both 24-2 or 24-2C. Here's the method to turn back on the false negative information, and here is how to get the fixation monitoring to go from just plain gaze tracking to include the blind spot monitoring. Since these should be available as a video to reference later on, you can come back and look to see how to approach those and alter your device. In addition, references from what I just described are here. These are the abstracts that were submitted to the ARVO meetings over the last couple of years. This one was Dr. Lee's on the global indices, and this is Sophia Yu's on the test times. Any additional questions, you're welcome to contact me at my email address here. Again, I'd like to thank my co-authors and thank you very much for your attention.
Hello, I'm Gregory Anderson. I'm the UX team lead at Carl Zeiss Meditech in Dublin, California. I will be speaking today on the effects of response style on SITA Standard 24-2C and SITA Faster 24-2C visual field tests. This is research that I conducted with Noah Alicia Graves at Carl Zeiss Meditech in Dublin, California. This research came about because of the first time I was administered a visual field test. It actually reminded me a lot of what is called a continuous performance test, which is a test used by psychologists to look at variables of attention in individuals. The reason there is such similarity is that both tests present visual stimuli at variable rates, which requires sustained attention in order to process the visual stimuli. The reason that the continuous performance test is administered is because people can vary widely in their ability to sustain attention. One of the common findings is that as task durations increase, vigilance decreases to a different degree in different people. When variably presented stimuli are used for visual field testing, there is an assumption made that missed stimuli are due to visual field deficits. But in some participants, attention difficulties may be a contributing factor, especially in longer test durations. And since people's attention is variable over time, attentional difficulties could also be seen in test-retest reliability. So how do we measure sustained attention? The primary tool used by psychologists is a class of tests called continuous performance tests. These tests measure response style and detectability over a 15 to 20 minute period of time. The test used large central visual stimuli, which removes visual field perception as a factor. Multiple measures are taken, including average response latency and detectability. One of the insights provided by the results of the interaction is that we do see an impact on rate of presentation on response latency and detectability. So that interaction is important for understanding people's response style and attentional variables. In this study, we looked at correlations between those variables and two measures of reliability on the HFA, loss of fixation and false positive responses. This chart shows the average response latencies of 10 participants. When we talk about response latency, we are talking about a continuum from a liberal response style characterized by faster average response rate to, as you might guess, a conservative response style characterized by greater latency between stimulus and response. As you can see here, the participants in this study showed a distribution along this continuum from a lowest average latency of around 450 milliseconds to a highest average latency of almost 700 milliseconds. All of these values are within the normal range. What we typically see with this continuum is that people with a conservative response style make fewer false positive errors because they carefully consider each stimulus before responding. However, with a faster rate of presentation, these people may make more false negative errors because of the extra time they spend thinking about the previous item. Conversely, liberal responders get in kind of a response groove, so to speak, and tend to make more false positive errors because they're focused more on speed than accuracy. Here are the data comparing visual field test errors on the HFA with response latency on the continuous performance test. On the left, we see a strong negative correlation between response latency and visual field test errors, meaning that the slower responders on the CPT made fewer errors on the HFA. On the right, we binned the participants into fast and slow ends of the response continuum to compare the two groups. As you can see, the fast responders' average latency is below 520 milliseconds, and they made an average of almost 4 errors on the HFA, while the slow responders averaged only 1.4 errors. So in this study, we saw that participants with liberal response styles showed a greater number of errors on the two visual field tests than participants with a conservative response style. And as we would expect, given the literature on the effects of duration on variables of attention, we found that people made fewer errors on the shorter SITA Faster 24-2C than they did on the standard version. In fact, only those participants with latency scores more than 1 standard deviation below the mean made any errors at all on the SITA Faster test. These two findings suggest that for some patients with highly liberal response styles, the SITA Faster visual field test will yield more reliable results than longer visual field tests.